think that parts of this work, or at least, have been already presented here in the past. So I will try today to give you an insight on the modeling and on the numerics that we do. So to start with, what we are trying to do is, in effect, write down a mathematical model to describe a particular motility of cells. Motility of cells that is lamellipodium based. This is a work that has started some years now in Vienna in the group of Christian Schmeisser, and parts of this work have been done in collaboration with him, with Dietmar Olds, Angelika Marhart, and Vic Small. I should also acknowledge several institutes that they have been funding our work in this direction. Like, of course, the university where I come from, the Johannes Gutenberg-Universität in Mainz, the RICAM Institute in Linz and in Vienna, the University of Vienna, and the Alexander von Humboldt Foundation. I would like to put it a little bit more in context, so before I focus on the details, I go a little bit out and I say, yes, what we are looking for is, as pretty much everybody else, to understand cancer dynamics in different scales. For that reason, we have approached our problem, first of all, macroscopically, if you wish. This is the work that we do in Mainz with Marija Lukachova, Niklas Kolbe, Bettina Wiebe, Nadia Hellman, and Jana Katutsova, and Müller-Klieser being our experimentalists. For this work on Thursday, Niklas will give a talk of our efforts in this direction. And today I will be focusing on the what we call atomistic scale of cancer cell motility. So, somehow, as I said, let me take it from the beginning. What type of motility are we interested in? In this experiment here, you see a white blood cell chasing a black bacterium. It's black because it's there, right? In between red blood cells. So I would like to focus a little bit on how the cell is moving. So this is the main body of the cell, if you wish, and I would like to draw your attention in the front. This a little bit thinner and more transparent structure is what is of interest for us. It is called lamellipodium. You might see it there in front of the cell, and you might see at the same time the bacteria has been going out of the direction of the cell. So what one would expect is that the cell turns and chases the bacteria in the correct direction. As a matter of fact, this is not what happens. What happens is the following. The cell builds a new lamellipodium on this side, dissolves the lamellipodium that has structure in the front, and the new lamellipodium pulls the cell to the left, as you can see now. At the end, at least here, the bacterium is captured. Now, maybe here, now that we have put it a little bit in context, we can see some cases of a fish keratocyte moving with the assistance of the lamellipodium that you can see here in the front. Maybe I should be a little bit more careful and say that the lamellipodium constitutes this very thin, very transparent and white region over here. The rest is the lamellum. Okay, we focus in the front. This is a melanoma cell, and you can see how it senses its environment with a lamellipodium. I continue with two more now. How it works? It works as follows. The cell sits in the middle in this rotationally, may I call it rotational symmetric case, and adheres to the substrate all around in kind of a rotational symmetric way. In some sense, pulls itself the same way from all directions. As soon as the symmetry of the lamellipodium breaks, the effective force pulling to the side prevails and the cell starts moving. The break that is of symmetry is of interest of us, and how the motility is induced. Like after the motility, after the symmetry has been broken and the motility is kind of constant in this case of a fish keratocyte. So this is our object. Okay, lovely. Now, how does it look? If you freeze the cell, take off the membrane, what you see is a very dense and focused really here in the front, a very dense meshwork of actin filaments. Actin filaments are double helices that they are quite long, of this order of magnitude, and they are quite thin, but they are still double helices. They pile on top of each other here, creating kind like a 100 nanometer of thickness of the lamellipodium, less than that, let's say 50 to 150 nanometers, which it is far less than the average length of the actin filaments, which is far less than the average size of the lamellipodium on the other directions. So in effect, you can consider it as a two-dimensional structure. But nevertheless, it is three-dimensional, so you can really scan through it with these tomogram images and identify the filaments as being here these black canyons. So what you do, if you're an experimental biologist, you go through each one of these pictures that presented here in this animation, and you point by point identify filaments, right? Identify filaments, and then the data from point by point filament identification, you give it to us, and we reproduce a small part of the lamellipodium to see how it looks. Over here, first of all, please note how thin the structure is, and we have done some work justifying the two-dimensionality, if you wish. Please also note how dense it is, although many filaments are missing. And let me point out that the blue nodes are just the points that hand by hand biologists have identified. To that extent, works that has taken place in Vienna had to do also with the image processing of the thing and the automatic identification, reducing the work to identify lamellipodium from 2 weeks doing that by hand to a few minutes doing that by a computer. Nevertheless, you can see here how dense this meshwork, and let me tell you that I have specifically reduced the radius of the actin filaments here to half the regular diameter. So they should be twice as thick as they are. Good. Okay, this is our constituents, this is our components. How do they behave? We know already that they build a dense meshwork with each other. In effect, particular proteins sit on two filaments, or if you wish, if two filaments are brought close to each other, particular cross-linker proteins attach to both of them, and they assist in the stability of the meshwork by providing stretching and twisting, resistance to stretching and twisting. That is, two filaments that have been attached with each other by a cross-linker resist to stretching and to twisting. These proteins have a preferable angle of 70 degrees between them. 70 degrees as you are looking towards the membrane, because the other is, of course, not 70. Good. We include that in our model. Now, what happens inside a cell, mechanically if you wish, is a kind of internal business. You need some mechanism to transfer the dynamics of what happens inside the cell to the environment outside. And this happens with proteins that are transmembrane and connect the meshwork, the actin meshwork that you have inside, to the extracellular environment. These are integrin. The main component of these proteins, it is integrin, and it works as follows: like an anchor that it is thrown from the cell, attaches to the substrate as long as it finds a proper environment to attach to, right? And then resists in the stretching, that is, as soon as the anchor is attached, it resists to the stretching by unfolding itself several times. This is how this thing works. This is another component that we have included in our discussion. Myosin. We have already heard about myosin these days, and this component is also in our system in the following way. As we said, we focus on the lamellipodium, which is a very thin structure in the front of the cell, which nevertheless communicates or is connected to the rest of the cell. An intermediate part is the myosin bundles. is the myosin bundles. So what are the myosin bundles? There are many myosin molecules attached to each other that create a very long bundle of myosin molecules that on one hand attaches on the lamellipodium and on the other hand on the lamellum. We include two types of myosin, myosin 2 and myosin 5-6, depending on the definition of from which school you come from, if you wish. That serves two different purposes. On one hand, as I said, creation of a bundle that connects the lamellipodium with the rest of the structure, and on the other hand, the myosin molecules advance on top of the actin filaments, bringing them together. We will notice these dynamics in a while. The motility, though, of the cell comes from the polymerization of the filaments. What is this process? This process is the elongation of a biopolymer by addition of new monomers on one side. So you have your polymer here, which becomes longer on one side by addition of new monomers, and at the same time, by depolymerization on the other hand, it shifts macroscopically to the left. This is where the energy for the motility comes from. This component also is included in our work. I wanted to present only 4 of them, but there are many more things that we discuss and we address, and we include nucleation, that is creation of new filaments, branching of filaments. So branching of filaments is how a new filament emanates from a new filament by a new branch. Capping, segmentation, and so on. I will come to more details in a while. Modeling wise, we start with the assumption that you can see over here. We make the assumption that our filaments are divided in 2 categories, black and green. The black filaments have a tendency, they turn to the right. The green filaments, they turn to the left. This is justified by the fact that the cross-linker between the filaments has a preferable angle of 70 degrees, which has been statistically also verified. And in effect, actually, the filaments can be divided in these 2 categories. So in our model, we include 2 families. One family we call plus and the other minus. And what do? We do the following. Each one of these families projects the computational space, if you want to discuss about computations directly, in any case, projects to the physical space, and the image of each one of these families is nothing more than one of the actin filaments. That is, each actin filament is the image, each actin filament being characterized by an index that goes all around the circle and by an index that goes through its length, is the image of a space from one family between minus pi and pi and minus L and 0. So we can, this way, with a single function, create a single filament, a single family of filaments. In particular, each one of these families can also be addressed now from a potential energy point of view. To that end, I refer to the following. It is known that the filaments resist to bending, and this has been computed already in the past. Each one of these actin filaments, has been bent with optical tweezers, and its resistance to this bending has been computed and measured. And we include that in the model by considering a Kirchhoff energy potential that you can see here via the square of the second derivative. The bending energy of the full system of all the filaments can be included and is included in the model by integrating over both families in both variables. The variable that counts the index of the filaments and the variable that counts along the filaments. In effect, counting all the bending energy of the filament.
Before you move on, you say there your G plus or minus. You've got 3 intervals, minus pi, pi, minus L, 0. What's the 0 to infinity?
Right. This is time.
Thank you.
At time t, the position of the, and I should have started from there. So at time t, the position of a filament is characterized by its index and its counter S along the monomer. And the bending energy is given by the total, as I said, Kirchhoff here, bending energy. So this is a simpler case. More complicated case is the adhesion with the substrate. How you work through that? You work through that with the following assumption. At a given time, in the past, T minus alpha, a cross-link or a connection to the substrate was created. On the filament A and on the monomer given by this index over here. That was in the past. A little bit later than this past, that is in the present, right? The same filament and the same monomer has been moved to a new physical position. Of course, the full discussion is how you include the numbering, the indexing of the monomers along the filaments. As we said, the filaments polymerize on one side. In effect, the actual index changes with time. And this is what we have included here. So the monomer that has been characterized in the past by this index is exactly the same monomer as this monomer in the present, which of course has a different index. The physical position has changed, probably because you have tried to grasp the cell and move it to another physical position. That is, the corresponding connection to the substrate that was created in the past has been stretched to where you are now. And this is the stretching, the actual stretching that you have included with the connection to the substrate. You include all this information here in this alpha, where on top of that, what you address as well is the creation and the breaking in a stochastic way of these connections to the substrate. So to put them all together, the connections to the substrate are created in the past, they are stretched, and this is completely computable, and they are created and broken with an age structure model, if you wish. I could come to more details. With an age structure model that addresses the rate to which they are created, they break, and they die with time. If you address and if you integrate, once again, if you sum up all this information, what you get is the total stretching of all the crosslinks that you have created in the past. And this creates the stretching, includes the stretching of the stretching energy of the adhesions with the substrate. You continue the same way and address now the twisting of the cross-linkers between the filaments. As I said, the filaments might be connected or not with a cross-linker. You include that with a probability kernel or with a probability stochastic, once again, term over here. And it has a preferred angle. If you twist them, this preferred angle deviates from the equilibrium, and in effect, the equilibrium is zero, and in effect, this provides with a force that needs to restore back to the previous situation. So back to the equilibrium. The same is the case with the stretching between two filaments. So you take again two filaments, you connect them with a cross-linker, once again with a probability that is given stochastically, right? To be created and be broken. And you take them away, you take them apart. So you can see how you can compute that here. So in actual time t, the two filaments, A plus and A minus of the two families, hence plus minus, were connected to the monomer SA plus and SA minus. And this stretching that you have created, that you have introduced, creates a restoring force. This is how you compute the stretching energy. And you continue this business over and over again, over all the potentials that you have taken into account. So far we have included up to 10 different potential energies, right? And here only some of them, right? And you sum them up because you use the first principle of superposition. So this is where you make the big modeling assumption that your system satisfies the superposition principle, right? And you complement this information, this system, if you wish, You complement it with the additional information that two monomers with each other cannot be taken apart if they are parts of the same chain. So within the biopolymer, you cannot take them apart. Inextensibility. And we include this information by the arc length restriction over here. Okay, so first, if you want a take-home message so far, first modeling assumption, big modeling assumption, superposition principle. Second, minimization. Once again, you refer to the basics, to the basic understanding of physics, if you want. If I'm not allowed to say something more than physics, so I stay there. So the basic understanding of physics that your system should minimize the total energy. And this is what we say. We count the total energy that the Lamellipodium includes, and we minimize it. Of course, you cannot do that numerically. It's inevitable that the computation will take for years. So you do calculus of variations. And from the minimization problem, you extract the corresponding Euler-Lagrange equation where you can track down the terms that you have put before. So in the bending, we had the square of the second derivative, which by the variational calculus gives rise to the fourth order derivative that you see here, and in effect our model is a fourth order model in terms of diffusion. So not second order diffusion. You might as well see here that the time derivative is incorporated through the material derivative of the system, accounting for both the movement of the cell and the change of the index that occurs due to polymerization. So the material derivative encodes the information that you attain due to movement of the cell and due to the change of the indexing of the monomers. All of them, they give rise, as I said, to a fourth order delay system. Good. So, may I come once again here, I think it's preferable, and point out a parameter that I have not addressed yet, and this is this eta parameter. What is this eta parameter, or eta function if you wish? This eta function addresses the length distribution of filaments, so how big they are. When we saw the first, some of the first videos of the moving cell, the symmetry was breaking of the cell and the cell started moving. What in effect means breaking of the symmetry is that the Lamellipodium changed its size from one side. It became thinner from one side. Thinner Lamellipodium from one side means inevitably less adhesions with the substrate and less of a force transfer between the cell and the environment. We account for the size of the Lamellipodium with this eta function here. You can see that in more details in the domain of the two families. So the filaments, as you go all around the Lamellipodium, are not necessarily of the same length. In one side, as I said, they can be shorter, and on the other side can be longer. This we include with a domain that it is not uniform. Right? This is, of course, very difficult to include, not only from a numerical point of view, but also from an analysis point of view. For that reason, we have included an extra function eta that performs as a cutoff where no filaments exist. So where the Lamellipodium does not exist as you go all around, the eta function performs as a cutoff. It is even more than that. It is the distribution, the length distribution of the filaments, how many they are, not only how long they are. So you might have more filaments on one side and less filaments on the other side. This is also included in this function eta. So it plays a very fundamental role in the derivation of our discussion. And I will try now to a little bit explain how it works. So here you can see a fictional one-dimensional membrane of a cell, all around red, and actin filaments going inside the Lamellipodium, inside the cell from the side. So emanating from the same region, there are filaments of different lengths. how the length distribution is with respect to how far they go. And this is the function eta. The function eta is the density distribution of filaments at time, of course, t, at the position, if you wish, emanating from the position alpha of the membrane, and how far deep the lamellipodium they go. This is encoded by S, where L is the maximum depth in which they go. We were yesterday, of course, confronted once again with this question. So how a distribution, how wide it is, but how it looks as well. So we have to address these two issues at this point. To do that, many things need to be taken into account. So I will not address all of them because this alone is a topic of a single talk. We have tracked them back, though, to the corresponding proteins that are included in this discussion, and today I will only refer to the capping and severing of the new filaments. Now, I will not address directly eta at first, but its derivative, its spatial derivative, that is, I will address the distribution and not the density and not the distribution function. And we use a classical fragmentation model, as you can see here, where severing is the rate at which the filament is breaking at different places, encoded by this S prime. If you work down with kind of a simple fragmentation, let's say linear kernel, it is very easy to see, a linear with respect to S prime, of course, right? It is very easy to see that the rate at which this U function of yours works, so the density of the length distribution, right? It is given directly by a very nice and simple integral over here. On top of that, the capping works with a constant rate. Capping of filaments works with a constant rate with respect to, because of a particular density, which for the moment is unknown, a particular density of the capping protein within the lamellipodium. If you write these things down in this way, you can easily solve with respect to eta, and you can get out that the distribution of the lengths of filaments is an exponential one, starting from a value that is given on the boundary, and as exponential dies out as you go into the lamellipodium. Right. Okay. Of course, this is not really helpful because as an exponential distribution, you have to stop it somewhere, and we stop it at some eta minimum, and in effect, we can solve with the maximum by stopping in some eta minimum. We can solve for the maximum depth in which, and this is this L, in which the filaments go into the lamellipodium. So we reply also two ways. We reply on how it looks as an exponential curve and how deep it goes. And this result is according to the literature, not only by our results, but also by the literature. Another point, we had to cut off this distribution, the exponential distribution at some point, and if you don't do so, if you don't cut it off, and you simplify your life by taking a linear distribution, because you're free, it's your model, you do whatever you want. If you take a linear distribution, which dies out on its own at some point, then we were lucky enough that the code was crashing constantly. The numerics were crashing constantly, and the only way to make them work, even in the linear case, was to include a minimum cutoff in the past. Biologically, this is sustained, the minimum cutoff, by the fact that you cannot even identify the few filaments as they go inside the lamellum because they are no longer visible. After you fix the cell and you take off the membrane, you froze it, for example, take off the membrane, you cannot identify how deep they go. You can identify really how deep they go up to a point and what is their density up to that point, eta min. Okay, I spent a lot of time for eta only for one reason. That's the reason. The maximum length at which the filaments go inside the lamellipodium depends on the polymerization speed of the filaments, V. This is a result. We didn't put it in. It came out, meaning in effect, the higher the polymerization of the filaments, the bigger the filaments. The bigger the filaments, the thicker the lamellipodium of that side. The thicker the lamellipodium, the more adhesions to the substrate. And in effect, more momentum transfer to that side of the lamellipodium, meaning it moves to this direction. So yes, the size of the lamellipodium, depending on where you look at the lamellipodium, this counter is a counter all around the lamellipodium, is directly given by the polymerization speed. Good. Another model exists, and I will not come into that. Another model exists for V. That is, another model exists to address how the polymerization rate is given. That's another discussion. Numerics. To resolve the big model, we had to devise our own finite elements. The reason was that we have a smoothness that it is not uniform in both directions of the model. One direction is all around the lamellipodium, and the other direction is along the filaments going in. Along the filaments, we had this fourth derivative in space, in S, which necessitates higher smoothness. But all around the lamellipodium, we had really no constraint. We could not use the same order of accuracy at the same direction. So we had to create elements that are quite smooth on one direction and linear on the other. Extra difficulties, or may I say the discretization, a little bit, a few words about the discretization. Each family is discretized separately, so this is the green family, and the blue family is the other one. And by discretization, along the filaments, you create computational cells over which you put your finite elements or your shape functions that you consider. You take them and you put them on top of each one of these cells, creating your finite element space. Right? Okay, good. Difficulty. Since you discretize two families, we go this way, they never coincide, the discretization points of one family with the discretization points of the other family. Numerically, to solve this issue, we have to work a couple of years, actually, just for that part. Anyway, we successfully, because it turns out that it's quite complicated in terms of the numerics, we successfully did a kind of a second-order interpolation in both variables to identify and transfer information from the crossing points to the discretization points. No more about that. Numerics. Rotational symmetric case would be the first one. What do we see here? We see the two families over here. And as a matter of fact, with red is depicted the first filament of the first family. It's not really important what the red is. What we see polymerization and depolymerization happening at the same time, filaments. So the filaments elongate from one side and they get shorter from the other side, okay? Stretching and twisting between them, so there is this force that has the tendency to create a 70 degrees angle between them. Hence the initial condition being straight filaments changed and curved filaments came into the discussion. The curving of the filaments, at least at this point, this is a little bit old numerical experiment, was accepted by our biologists. We see adhesion with the substrate, friction with the substrate, and we see no membrane. So there is no membrane in the system. That is, there is nothing pushing or controlling the filaments to stay within the lamellipodium from the outside. There is, though, from the inside, myosin inner pulling force. So each one of these filaments is pulled to the inside. If you put them all together, they have the tendency to polymerize and escape the lamellipodium to the outside. They depolymerize at the same time from the rear. they are twisted due to the twisting force. Bending energy resists to this bending that the twisting force creates, adhesion with the substrate, and from the inside there is an inner pulling force. Good. Why do we need that? Chemotaxis. So what we want to see is how cells move in realistic situations. How does it start? We consider here a cell, as you can see all around. The thickness of the lamellipodium is similar, and we have included in the system a chemotactic signal stronger from this side. Actually, the strongest, the highest point of the chemotactic signal, it has been prescribed not in the environment, only on the membrane. Higher here and less all around. Okay, higher in this direction. The effect is as follows. Due to the stronger chemotactic signal from one side, the polymerization rate from this side is stronger. The lamellipodium becomes thicker from this side, it is thinner from the other side, the effective pulling force is towards to the right. Maybe I didn't point that out strongly, but I would do that once again. All the filaments, including the filaments that are here, polymerize to the left. They go to the left. Retraction, though, and symmetry break came as a direct result of higher polymerization from one side and the inner pulling force of myosin. Myosin force, being on the inside of the cell, has to sum up to 0 in the total force. Otherwise, the system is not isolated. And this is what you see here. The total inner pulling force is equal to 0, and the higher propagation, if you want, to the right prevails, and the rear is pulled along to the right. So, higher chemotactic signal to the right. What happens if you change it? So, higher to the right, and then we twist it. We put it on the top. You can see that the lamellipodium has deformed already. So here, as before, the thicker side is to the right. Due to the change of the signal, the thicker side comes to diagonally, whatever that is, and it takes some time until the lamellipodium restores this moving shape that we saw also before. We have compared the final moving shape when after it has turned and before it has turned. So when it moves to the right and after the turning when it moves diagonally, and the shape is after some time the same. So in effect, how much time do you need to perform such a turn, as we can see cells doing? We have a cell that actually turns and maintains its shape. How much time do you need? We can turn other cell shapes, not only like the one that you saw before. We can tell cells that have such a tail on the rear. Once again, the chemotactic signal is stronger from that side, meaning, as we have included, higher PIP3 signaling from that side, higher polymerization rate, thicker lamellipodium from that side, stronger the effective force to the right. Good. I said cancer, right? So I have to explain a little more later on. But you saw, in any case, two different moving shapes. How can we distinguish between them? How can we create different moving cell shapes? And this is the signaling as has been encoded in these three cases by the polymerization velocity. You see it is never 0 in none of the experiments. The lower the polymerization velocity, the more to the left is the corresponding image. And the relation between them is what gives rise to different cell shapes. The transition, of course, from one to the other is something that one can address. Is it smooth? Is it continuous? Right? These are things that you can work with, and you can restore your own moving cells. Oh, excuse me. I think that I need only 2 more minutes. You see? As I said, okay, we want to address cancer, right? What does that mean? It means chemotaxis, of course, is one thing. Haptotaxis is the other. What we see here is a cell which is attracted by a chemotactic signal that is on the right side. The substrate, being divided in white and red, is of higher and lower friction. The corresponding, as we said, so the integrins need to attach to the inside and to the outside. When the cell is on top of a region, on these integrins, we have set in a very low value the corresponding adhesion coefficient. So the adhesion coefficient is what we vary with respect to space, very low and higher and uniform. So here is uniform red, right? And the cell moves due to a stronger chemotactic signal from this side. This is the point. But when it reaches this white region, where no adhesions are, these parts of the cell cannot move anymore. They actually are dragged by the rest of the cell that goes on top of this higher adhesion region. The cell deforms. And after it's gone through, it restores its previous moving shape. That's for us. In effect, you can see how it works if you have a corridor, a higher adhesion corridor in this way, right? This is how the cell works. Now, two more experiments, numerical experiments. What happens if you take a cell and put it through a narrow corridor? As before, these parts are dragged by the rest of the cell. So we did these numerical experiments to compare with the things that Michael Sixt. So we expect now experiments from our biologists to do a direct comparison on these things. This is why we used such experiments, adhesion patches of this form. Now, the previous was a preparation for that. This is what we wanted to see, actually, how it behaves here. The numerical resolution at this point is very coarse, right? Because we do our numerics in laptops, actually, and of course we could do them in better machines. Anyway, the tail is of interest. What the tail, how it behaves here, of course, because it's dragged and the tail remains there. Okay, good. And this is somehow in very good correlation. Oh, excuse me, I forgot here the reference. 2013, CSUS SUS is pronounced, I think. SUS et al. Is the proper reference for this experiment. And where you can see also a similar behavior here. The tails of the lamellipodium remain, where the rest, which is on top of non-adhesive patches, moves alongside. I conclude by saying, how much? I conclude by saying that there are many things that we want and we are currently doing, and I will not refer to them. I will only refer to one, EMT in cancer cells. So thank you very much. Thank you very much.
Questions quickly at the back.
I'm very curious, if you would offer an equal chemotactic gradient in both directions, does the cell keep on standing still? Does it split in two? Or is the symmetry breaking causing it to move in the right direction?
You mean left and to the right?
Yes.
Can you please tell me what happens in the middle?
Just like a gradient that it wants to move left and right.
Then it deforms like it was over there, kind of a peanut shape.
And then it will stop?
The numerics at some point they break, but I have not driven this experiment to... But it looks like that, a little bit, right? May I say that there are many things that we want to do and we are thinking about doing and we are doing. I only refer to one of them, but we are constantly open to ideas, suggestions and discussions on these things, right? It is something that it is...
in view of the time, we should, well, there's coffee outside, so we should thank both speakers. Thank you very much.